So, in this lecture, what I want to cover is some of the physics and chemistry that determines both the bulk and surface properties of materials. So that when we talk about the individual materials, like metals and ceramics, and some of the things that we've already done with polymers in previous lectures, we can start talking about them in engineering terms relevant to our field. Also, talk about some of the ways that we measure these physical and the bulk properties of materials so that especially when we start considering the design process, we can start using engineering parameters that other engineers can test for and determine the success or failures of these devices. So first up, I want to talk about materials at the atomic level because I think the key to understanding the bulk property and surface properties of materials is actually figure out at the atomic level how things are put together, and then we can start looking at macro levels from there. So, in the entire universe, we actually only know of four attractive forces, and they are gravitational, both the weak and strong nuclear forces, and then all electromagnetic forces. Now, of these forces, we can categorize them based on the distance that they act on each other and the order of masses in which they act on. So, gravitational forces, I think everyone has a very intuitive understanding of that. It's what holds us to the surface of the planet. It holds moons close to entire planets. So we can understand that it works on incredible distances and on very large masses. But if you consider the potential energy of something like two argon atoms in the vicinity of each other, many orders of 30 orders of magnitude weaker than any comparable intermolecular force that we might act on an atomic or molecular level. So it really doesn't have any bearing on the bulk properties of materials. Both weak and strong nuclear forces are incredibly powerful, but only on the subatomic level, something on the range of 10 to the negative 4 nanometers. So that doesn't explain how atoms or molecules are held together. For that, we need to look at electromagnetic forces, which manifests itself in a number of different ways. Van der Waals forces, for instance, explains the interaction of atoms or molecules that each have no exact dipole moment, which means that there's no positive or negative face or side to a particular molecule. These forces explain a number of different things at a number of different size levels. So, for instance, the way argon atoms interact with each other, polyethylene polymers that have no obvious dipole moment, and also lipids, like in the cell membrane bilayers that tend to self-assemble and interact with each other, even though they themselves don't have a dipole moment either. I remember descriptions of ionic and covalent bonding back to my high school chemistry days as ionic being the donation and receiving of electrons. So one atom gives up permanently an electron, whereas another atom receives it. So I think of examples like sodium chloride crystals that form ionic bonds. Covalent bonding is kind of the opposite. It's when electrons are shared instead of giving one up or receiving one up permanently. Classic example is any organic compound where we have carbon-carbon bonds or cross-links within polymers. I think of hydrogen bonding as sort of the opposite of van der Waals forces, where in hydrogen bonding you have dipole moments, where atoms or molecules have sort of sides to them that are either positive or negative, and the attractive forces between negative and positive sides creates a sort of bond, and that's what we call hydrogen bonding. See it a lot in water, so obviously it has large implications in biomaterials because we're so water-based. And then metallic bonding, I'll again remember some of my descriptions from high school chemistry as the sort of lattice structures of the charged nuclear cores that are surrounded by a sea, quote unquote, a sea of electrons that have the ability to interact with all the nuclear cores of that particular metal running through the structure. The table on the left also demonstrates the relative strength of these electromagnetic forces in comparison to each other, and then the amount of energy that's required to break that typical bond. So like I say, I think of van der Waals forces and hydrogen bonding as similar in mechanisms, just acting in the exact opposite manner of each other. So their bonds are relatively comparable to each other. I think of the same thing for ionic bonds and covalent bonds. Ionic bondings having the permanently giving up or receiving nature of the electrons, making them a bit stronger than covalent bondings, which only share. And then finally, metallic bonding, which is kind of right in the middle of ionic and covalent. And we can closely approximate the typical binding strength of metallic bonds through the heat of sublimation, so the heat that's required to sublimate a metal. We then understand that we can use these electromagnetic forces to form molecules from combinations of atoms, and that the bulk properties of these materials that make up these molecules is dependent on the arrangement of these individual atoms and molecules. So, for instance, I think it's intuitive to understand that a typical helical shape of just a single collagen fiber would break under just a few nanograms of support because it's just not meant, the intermolecular forces aren't able to withstand that amount of force. Yet, if we arrange them in this really complex hierarchical formation that makes up the tendons in our body, then all of a sudden we can support many kilograms of force. It's incredible how strong our tendons and ligaments are. Now, on that note, I'm going to use that to segue into how engineers actually measure and talk about the strengths of these individual materials, whether or not it's a single collagen strand, a complex ligament. Let's talk about how we measure that. Now, properties of materials can be divided up into two categories. One would be surface properties, and the other would be bulk properties. Now, the surface properties are important because they dictate the interactions between a material and its environment. So they have huge implications in the biocompatibility of a particular material. But the success of a material also depends on its bulk characteristics, so how the material acts on a whole homogeneously throughout the entirety of the material, not just the surface. And a really easy one to imagine, I think that's intuitive for most people, are the mechanical properties, things like strength, ductility, toughness. But there's also more unique considerations that are attributed to the bulk properties, like thermal, optical, electrical, that come into play for some very unique biomaterials. Now, bulk properties themselves can be divided into two different subcategories, one being called intrinsic and the other being extrinsic. Now, for intrinsic bulk properties, we just have to realize that the properties of that particular material depend only on the composition of the material and not on the structure. And what's most important and an easy way to determine if it's intrinsic or extrinsic is whether or not it depends on how much mass you have of that particular material. If it's independent of mass, it's intrinsic. So examples are the heat capacity of material, the temperature, and the density. You can always take a piece of metal and cut it in half, and it's going to be just as dense. It's going to have the same temperature as it has before, the same heat capacity. Whereas other properties that are extrinsic, that depend on the mass, are going to be halved or doubled if you either half the amount of material or double that amount of material. So examples, and some of these we're going to cover in just the next few slides, but things like yield strength, mass, obviously, volume as well. And what's nice about this, especially when we're designing materials, is that because some properties are intrinsic and others are extrinsic, we can isolate and optimize many different properties of biomaterials simultaneously by maintaining the intrinsic properties that we want and then shaping a polymer because we know those properties aren't going to change as we change the mass, and then optimizing the extrinsic ones according to the size or needs of our particular material. Now, because mechanical strength is a bulk property that's easily understood and also vitally important to biomaterials, we're going to talk at length about a number of different mechanical properties and ways of quantifying them in the next few slides. So the first thing I want to cover are the concept of stress and strain. Stress is a way of quantifying the force on a particular material normalized to its respective area that that force is acting on. Now, in this case, because force is a vector, we have to differentiate nominal stress, in which case the force is normal to the applied area plane, and shear stress, in which case force, the vector, is parallel along the plane in which that force acts. Now, in both cases, the units are going to be the same as any unit of pressure. Typically, I see pascals or newtons per square meter in SI units. And any stresses that are oblique or in between either of these are simply divided into these two separate components whenever discussing stress versus strain curves. Furthermore, because stress is a vector, we also want to consider whether or not that force is pulling, in which case we call tensile stress, or pushing something together, which we call compressive stress. Now, in all cases, whether it's nominal stress, shear stress, compressive, or tensile, we also understand that the area on which the force acts is going to change over time as you deform a particular object. So usually, like in the case of the nominal stress, you just normalize it with respect to the starting area. You can also use what's called true stress, which takes the instantaneous area that changes over time, but I see that less often in simple biomaterial testing. The other aspect in a stress versus strain curve is, of course, strain, which is the measure of the direction in which you pull or push these materials at. Now, in the case of nominal strain, strain is defined as the percentage of the change in the original length which you either push or pull at. So, for instance, if you were to compress something to half of its height, then the numerator would be one half of the original starting height, so you would have a strain of 50%. And in the same way that if you were to elongate something by twice its size, you would have a strain of 100%, meaning that you doubled the length because you pulled it under tensile forces. I less commonly see the extension ratio, here written as alpha, in literature or mechanical studies, but it's pretty easy to figure out because a strain is just equal to the extension ratio minus 1, or simply it's the resulting length of your sample divided by the original length. For shear strain, because you're sort of shearing an object, you don't quite have the same length dimensions in which to work with. So in this case, shear strain is defined as the tangent of the angle normal to which you're shearing from. Okay, so a 0-degree angle will represent no deformation whatsoever. And then if you can imagine, a 45-degree would be quite an extreme amount of shear of that particular object. Now, the way you would use these pieces of data are not in individually reported values that you would see in a table, but instead plotted on what's called a stress versus strain curve. So here you can imagine that the raw data you would get from mechanical test would be the force that you act on a particular area, and then also the amount of extension or deformation that you occurred, and then accounting for the size of a particular sample, so in that case the area in the case for stress, and the amount of elongation or compression in terms of strain or angle for shear strain. You would then convert those raw values into treated stress versus strain values, in which you would report here, where stress is the y-axis and strain is the x-axis. Now, what's great about this particular graph is that there's so much information you can get from this type of graph. So we're going to cover a lot of the different components and calculations you can do from this kind of data. And the first I want to touch on covers within the scope of what's called elastic deformation. Now, what elastic deformation is the amount of deformation that a material can withstand while still being able to, and I'll say bounce back. Whenever I say elastic, I think of things bouncing. And if you can deform something only to a certain point where you know it can withstand that amount of deformation and then bounce back to its original shape, it's called elastic deformation. And we'll also talk about inelastic or plastic deformation, which is where you deform something so much that you permanently alter it and then it can't go back to its original form. Now, in this particular graph, we can see that the elastic deformation stage is in the sort of initial, I've outlined it in the red box, and it's shaded, I think, in a teal or a blue color. But that's where the amount of stress is linearly proportional to the amount of strain applied. And so whenever you get past that into the plastic or inelastic deformation, those are synonyms, where the stress is no longer proportional to the strain. That's where the curve starts to kind of meander off. Okay, so whenever we see that linear line, we know that we're in the elastic deformation stage, and then whenever it's no longer linear, then we know that we're in plastic deformation. Now, within elastic deformation, the most commonly reported value I see is the Young's modulus. So that's almost the most important piece of information that you can take away in that graph. And what that is, it's the slope of that linear line. So it kind of dictates how proportional the stress is to a particular strain. And the steeper it is, the, I guess, stronger that material is, for just a lack of a better word. So I want you to think of this linear region as just simple y equals mx plus b lines. In this case, b is 0. There's a 0 intercept in this case. Y being the stress, x being the strain, and then the modulus as the slope, m. So in this case, Young's modulus is usually what we refer to in either compressive or tensile nominal stresses. And then in shear modulus, we have this term G, which is just the shear modulus. A term I see less commonly is something called the bulk modulus, in this case designated as K, where just pressure, P, general pressure applied to a particular object that deforms it, can change the volume. In this case, volume is sort of taking the place of the elongation change in a particular dimension. In this case, it's incorporating all three dimensions. So that's why V2 minus V1 over V1 looks very much like the strain equation in just one dimension. So think of pressure as taking the place of stress, volume as taking the place of elongation, in which case you can calculate this sort of pseudo strain curve, and then K as the bulk modulus. And then once again, I want to stress that this is only within the elastic deformation stage. The fact that it's proportional also implies that this particular linear relationship is reversible. All right, and that's the exact definition of what elastic means, is that no matter how much deformation within the elastic stage you apply, that material is going to, and again, I'll say, bounce back. So there's no such thing as a modulus within the inelastic stage. Another aspect that we can touch on that isn't represented in this particular curve is a concept known as the Poisson ratio, which is the strain in one particular direction, whatever force that you're acting on, divided by the strain in the opposite normal vector. So if I think of myself as pulling on, say, a steel rod, a steel cylinder, I'm going to pull it and elongate it in the direction in which I'm pulling, but it's also going to get thinner along the diameter of that rod. So the Poisson ratio is a way of calculating the change in shape in the longitudinal direction, in this case the diameter, with respect to the transverse elongation. Now, because that change would tend to be the opposite in most materials, just like in the example I gave where you're elongating one end and then shrinking in the opposite direction, or I say opposite, the normal direction. There's the negative sign in there just to give us a convention of having positive values for most materials. There are also some materials that actually have a negative Poisson ratio, meaning that even as you elongate a sample in one particular direction as you're pulling or compressing it, it's actually going to get bigger in the opposite direction as well, but that's not common. So now we get into the plastic deformation stage. So now this is also synonymous with inelastic deformation. They say the same thing. The definition of which is just that there's irreversible deformation from which the material does not recover even after the removal of that stress. So again, having that linear relationship in the elastic deformation stage implies that it is reversible. Plastic deformation now means that we're getting into the irreversible deformation, which for most cases of biomaterials, you would not want to subject it to. So if you imagine having a hip implant, you always want to have a material that has that stays within the elastic deformation stage, so that no matter what mechanical stresses is subjected to it, it can always recover and just act just as it was before those mechanical stresses were ever induced. So the first thing I want to touch on for the plastic deformation is the proportional limit, which is the stress at which plastic deformation begins. So again, here I say stress. It's not a strain value. It's the amount of stress that it takes that a material can withstand before converting to plastic deformation. Now, the one thing that's tough about this is that the proportional limit is really a theoretical value. It's the exact pinpoint in which that plastic deformation begins. So on a molecular level, when the first bonds start breaking or being irreversibly damaged, as you can imagine, it's really tough to pinpoint the exact moment in which a molecular bond breaks. So what engineers usually rely on what's called the yield strength, which is where the quote-unquote noticeable deformation begins. And a lot of this can be dictated by at what point you, what the resolution of your data is. But for instance, like metals, whenever we see a 0.2% change in the expected strain or expected stress from the linear region, then we start calling that the yield strength. Next up, we'll talk about plastic strain. So plastic strain is simply the strain within the inelastic or plastic region. And the way you find this is by drawing a line parallel to the elastic region and then finding the x-intercept along that line. So if you can imagine, if you're anywhere within the elastic region, your parallel line is going to be exactly on top, and thus your plastic strain is 0%. As soon as you get past the yield strength or the proportional limit, then you're moving into small fractions of the plastic strain. And a very important exact parameter within plastic strain is called ductility, which is the plastic strain that's taken at the breaking point of your particular material. So if you can see at this curve I can imagine is taken until that particular material actually breaks, and then you're no longer compressing or pulling. In fact, this is a tensile test, I can tell, because you're pulling something apart. As soon as it's broken, you end the test, and you can get ductility by finding that sort of parallel line And it's even written here as a dotted line at the very end at the breaking point, which defines the ductility, which is a specific plastic strain. Other parameters that are labeled here that we want to talk about are the ultimate or the tensile strength of a particular material. So that's the absolute maximum peak point on a particular curve. So you just look for the maximum value, and that's the ultimate tensile strength. There's also the breaking point, which in this case is very often lower than the ultimate tensile strength. It's whatever point on that particular material that it just took to finally break it. Sometimes materials don't just have a clean break, they just start to tear. And at that point, you want to end the test. So this is usually the very first point of noticeable breaking. There's no point to actually completely tearing or separating material apart like when you're pulling it. You just identify the very first point in which the material starts to break. There's also two very important points of integration within a stress strain curve. The first is the resilience. So resilience is, to me, I think of resilience, I think the ability to withstand something and still be able to bounce back. So again, invoking that term of elastic and non-plastic deformation, resilience is just the area underneath strictly the elastic portion of a stress strain curve. So in this case, the green shaded area. So it's also called elastic energy. Toughness is, again, I think of a very layman's description of toughness as to be able to withstand any sort of pressure and not break. And I think that's very applicable to this graph as well. It's the area underneath the entire portion of a stress versus strain curve. So in this case, green plus yellow. So it's the elastic plus inelastic energy. And just as their name implies, these are units of energy, right? So it's stress versus strain. We're integrating, so we're multiplying stress by strain. If we think of our SI units, stress would be in newtons per square meter. Strain might be in meter per meter. Remember, it's a percentage. So force, newtons, times meters is work. So this would be in units of joules. And then the denominator in this case is the square meters of the area times meters, in which case you elongate or compress something. So that'd be a term of volume. So this is energy per unit volume of a particular material. So we know that this is an extrinsic property. If you double the size of material, of course, it's going to have twice the resilience, twice the toughness, and it's going to be able to withstand more energy before it breaks. Next up, so on this graph, there are 4 different materials that are presented on a typical stress versus strain curve. And we can see how all these different materials have different properties. We can even start thinking about how they have different amounts of ductility, resilience, and they're typically representative of different types of materials. So I'll look at something like material 1, and I see something that's very brittle, meaning that, yeah, it has a certain amount of resilience, it has elastic deformation, but before it can even start deforming in the plastic deformation stage, it just breaks. So I think of something like a ceramic. Whereas I look at something like material 2, just like we had on the last curves when we were talking about stress versus strain curves, and I think of something like a metal. Okay, it has elastic deformation, then it starts to go into inelastic, and then after a while it becomes fatigued so much that eventually cracks and breaks. Material 3 and 4s are a little bit interesting because they both have, yes, elastic regions, and then they have dips in other regions where finally they begin to spike up towards the end again. So a lot of polymers, I think, exhibit this type of material, these type of behaviors, just because polymers can come in a variety of different compositions. They experience phenomena known as necking, where you can actually align polymer chains in particular directions. This is something that you can't do with other materials because they don't have these really long chains of materials. Something like a metal is just simple ions within metallic bonding grouped together. So polymers, you can elongate chains, and as part of that elongation process, that results in a dip of these curves, and then once they're finally elongated, they kind of get their second wind and they get a little bit stronger, and then you see them pop and spike back up again before ultimately breaking. A few last things I'll cover when discussing mechanical properties is that the strain rate, so the speed in which you deform something and that strain changes, affects data and materials. So it's very common to have defined standards of strain rates in which you would test something. So a value that I see very common in literature and ASTM and ISO standards is to compress or tensile test something at a strain rate known as 100% per minute, which means I'm going to compress or pull something at a rate that's equal to its original height every minute. Now, you might not go to 100%, meaning you're not going to squish something to an infinitesimally small disk or pull something to twice its height within that minute. You might only go to a 30% strain, but that particular rate is going to be normalized for every sample you take. So if you have a sample that's, say, 10% larger than the other, you're not going to compress or pull them at the same absolute velocity. You're going to make that proportional to the height so that the same strain rate is met between every sample. There's also some fancy tests you can do beyond just simple one-dimensional or one and done stress versus strain curves. So there's tests known as creep tests, in which a fixed and constant load is applied to a particular sample while strain is monitored. So you might initially compress something to 30% strain and then maintain that particular load that it took to get to that particular strain. So as a material starts to deform over time, you have to change the amount of strain in order to keep that particular load constant. And eventually you're going to break it either by compressing too much or tensile pulling it apart too much, because it eventually just gives up and can't resist that load indefinitely. There's also fatigue failure, in which case you'll do cyclic tests that you did for like a stress versus strain curve. You'll repeat that, you'll offload the amount of load, and you'll replicate it again to the same amount of strain. And eventually, over time, you'll start seeing changes in your modulus values that represent a fatigue in that particular material. So as you can imagine, as we're doing tests on artificial hearts or hip or knee implants, you want to make sure that your particular material can withstand millions of cycles, not just a single cycle in which you test the modulus once. Hardness testing is something you also see. In this case, you measure the material by applying a known load using a small indenter of a known geometry. I see pyramidal shapes or spherical shapes often. You put that in contact to the surface of the material, again at a fixed load, for a known period of time, and then after that you offload and you measure the indentation in your particular material, and that gives you an indication of hardness. Now, beyond mechanical properties, there's other bulk properties that are important to biomaterials, especially in very niche or unique circumstances, like thermal properties, optical properties, if we're putting in artificial lenses, electrical properties, and also even magnetic properties as well. So now that we've covered the bulk properties, I want to divert our attention to the other important aspect and properties of materials, which are the surface properties. As I mentioned before, what's really important about surface properties is that's the interface that acts with the body. So from a material perspective, biomaterials only show the world or the biological environment its surface, not anything within the bulk of the material itself. So in order to study the biocompatibility of a particular material, we first have to understand the surface and the interface of that particular material. So, and I just used that word interface a number of times, so I wanted to find a few key differences in some of the terminology that we'll be using here. The interface is really just the transition between two phases. So in principle, this could be an infinitesimally thin plane between two phases, where in reality, it's actually more of an interphase, which is a unique compositional zone with a finite and measurable dimension between two phases. So I like to think of it as bulk properties of the biological environment, bulk properties of the material, and in between that, there's an interphase which has very unique reactivity and surface properties. So let's talk about those surfaces and interphase a little bit more in detail. So there are a lot of unique aspects of surface properties that we want to consider whenever we actually analyze the surface properties of a particular material. So the first and foremost is that surfaces have unique chemistries that are different from the bulk of the material itself. And the way I like to think about this, especially as a trained chemical engineer, is that the surface of material works very much like how a catalyst works. Because a catalyst never shows up in the net result of a particular reaction, just like it doesn't affect the bulk properties of the biological environment or the bulk properties of the material, but it facilitates the interaction between those two in the same way that a catalyst does. Also, the surface of material is inevitably and inherently different from the bulk of it. Okay, we can't use the same ways of measuring bulk properties like stress versus strains on an almost different type of dimension like we will find on the surface. So we have to have unique ways of measuring it and consider it in a different angle than we would bulk properties. Part of that is because the mass of material at the surface is so much smaller than the rest of the bulk. So if we have an oxide layer on the outside of steel or a metal, that might only be around 100 angstroms thick. So it's certainly not enough to affect the hardness, resilience, or strength of material, but it certainly has its own properties in itself that we have to look at that are, again, much different from the bulk. And having just mentioned oxide layers, surfaces rarely contaminate and they change and they become much different from the bulk of the material. Okay, we have surfaces that are susceptible to proteins, ions that get infiltrated by the body. And so it even starts changing the chemical nature of the surface. Again, that's much different from the actual bulk of the material. And part of the reason that happens is that surface molecules exhibit considerable amount of mobility. If we have a complex polymer mixture that has both hydrophobic and hydrophilic parts of that polymer, if it's on the outside of material, if it's at the surface, it might align its hydrophilic properties so that that's interfacing with the hydrophilic environment of the body, whereas that would have a much different alignment in the bulk of the material. So molecules can change their shape at the surface in response to that in different ways than would occur in the bulk of the material. So taking those into consideration, there are a number of different properties of surfaces that one will want to measure that might factor into the biocompatibility of a particular material. So these could be the roughness of material, wettability, surface mobility, chemical composition, perhaps the electrical charge and how that might be different from the bulk of the material. And again, also crystallinity, which again could also be different from the bulk. So now that we've discussed some of those properties, let's talk about some of the analysis methods that give us quantifiable results for those particular properties. So the first one up is contact angle, which can give us a sense of the wettability of a particular material. Now, I've done contact angle tests before, and what's really nice about them is that they're so easy to perform. And looking at this picture, what we're really looking at is that you would take sort of a flat piece of material, you would literally put a drop of water on it, and then you would measure the sort of spread of that particular drop. And we've seen some very cool research into ultra hydrophobic materials that will produce almost a near perfect spherical shape of water because they're so not wettable that the water doesn't want to interact with the material at all. Other really wettable materials would have a really nice spread. And the way you kind of measure that spread is by looking at the contact angle, which gives this method its name, of that particular drop with respect to the surface, like you would see here in that diagram. And really what makes it so easy to measure is just it really consists of a camera that looks at the side of that droplet parallel to the surface, and then it uses image analysis techniques to measure that angle of that particular droplet. So it gives us a nice direct way of measuring wettability. Part of this that also factor into the wettability and the spread of that droplet would be the surface energy, the roughness, heterogeneity of that surface, the amount of contamination. So you would actually see changes in the spread of your droplets depending on how contaminated your surface is. And then also the molecular mobility, which would also change the wettability and contact angle of your device. The next two methods are both vital for providing qualitative and quantitative overviews of the surface chemical composition of material. The first one is electron spectroscopy, which I sometimes also see referred to as X-ray photoelectron spectroscopy. This one is based on the photoelectric effect, first described by Albert Einstein at the turn of the 20th century. And it really relies on complex instrumentation and vacuum chambers to bombard materials with X-rays. And then using the photoelectric effect, it can determine the elements present, the relative concentrations, and also the bonding environment of those particular materials. Now, ESCA has a penetration depth and resolution of around 10 nanometers, so it's great for maybe I'll say bulk surface properties, I guess a relatively large surface interface area. The second method, which is called secondary ion mass spec, is very often used in conjunction with ESCA. It has a higher resolution of around 1 to 2 nanometers of a surface. And in this case, it bombards the surface with positive ions and then measures the mass spec of whatever flies off with that. So I always think of breaking in a new game of pool where you send the cue ball and that breaks apart all these little balls. Depending on the scattering of those little balls, you can determine the chemical composition at particular surface, usually at a higher resolution than the electron spectroscopy. Next method I want to touch on is SEM, or scanning electron microscopy. In this particular method, an SEM unit will focus high energy electron beams that scatters whenever it hits a surface, and then the scattered low energy electrons that bounce off are used to render high image resolutions. So what people really love about this method is that, of course, it gives great pictures. Like, who wouldn't love a picture like this? I think, in fact, what we're looking at right now are, I think it's pollen. This is an image of pollen. And so all these other methods give data, give values, and people hate looking at charts. They like looking at pictures. So if you get SEM of your material, images look fantastic, and they give you a visual, a qualitative analysis of your surface. Next up, we have infrared spectroscopy. I always see this as Fourier transform infrared spectroscopy, so FTIR, which, when analyzed, reveals information about the particular bond formations and vibrations of materials. What I like about this method is that it's super easy to do. I know a lot of labs that have very high quality benchtop FTIR units. This is on contrast to electron spectroscopy and secondary ion mass spec, which require huge units. I know colleges that might only have one of each of those units, not individual labs like FTIR. So that's one great advantage of FTIR. The disadvantage of FTIR is that it's not very sensitive. The resolution is usually on the order of microns, whereas the other two units are on the order of 1 to 10 nanometers of a particular surface. And then the last surface property measuring device that we'll talk about is AFM, which is atomic force microscopy. So this actually makes use of a cantilever that is deflected based on the amount of van der Waals forces and other electrostatic forces that act upon it. So by measuring the amount of deflection using a highly sensitive laser that bounces off that cantilever, you can actually render images on the nanometer resolutions. So it's another great way of providing visuals to a particular surface. So now we've covered ways of analyzing, talking about both bulk properties and surfaces. But for now, thanks for listening. Bye.